The other obvious way that we could connect these capacitors is we could string them all together end to end. This is called capacitors in series. We want to know what equivalent capacitance could replace these three. To figure this out, the way to analyze it, connected to this battery, we know that the top plate of this capacitor is going to charge with positive charges. The bottom plate will become negatively charged. What about the plates in the middle? The way to think about this is imagine we could draw a green box around this and we just have a piece of metal shaped like an eye inside that green box. Inside the purple box, we have the same kind of piece of metal. These pieces of metal don't have any physical connection to the rest of the circuit, so they started off as neutral pieces of metal and they have to remain that way. So we have plus Q on the top plate here outside of the green box. Right inside the green box, this end of the eye will have minus Q on it. But if we've got minus Q here, that means we've left behind a plus Q down here. If there's a plus Q here at the bottom of the green box, there has to be a minus Q at the top of the purple box to match it. If we have a minus Q there, we've left a plus Q down here on the bottom of this plate. And finally, on the other side of the purple box, this must be minus Q. So what this tells us is all of these charges are the same size. The signs are alternating, but we start with plus Q, minus Q, plus Q, minus Q, plus Q, minus Q. The charge is the same on each capacitor. So the capacitances may be different, C1, C2, and C3, but the charge on each one is the same. This is the key result if we have capacitors in series. We can also realize that the potential difference between the top plate of the top capacitor and the bottom plate of the bottom capacitor has to be the same as the potential difference of the battery, right? Because they're connected directly. Now, if that voltage of 1, 2, and 3 altogether equals this voltage, we can write this. Battery voltage equals the sum of the voltages across each capacitor. Now we go back and use Q equals CV, and we realize that we can write all of our voltages like this. Q over the equivalent capacitance, which is what we want to know, equals Q over C1, Q over C2, Q over C3. Notice the Q's are all the same because we said the charge on each capacitor will be the same and the charge on the one that will replace them all will be the same. So when we have this, it's pretty quick to just divide everything by Q and we get this. This is how capacitors in series combine. We take the sum of the reciprocals of the capacitance and then we flip that over to get the effective capacitance. This means when we're done with making this capacitor, the effective capacitance is smaller than the smallest individual capacitance. So we might write it like this. The most common way students mess this up is to forget that there's that reciprocal at the end. So for example, let's say we have three capacitors, 40 microfarads, 60 microfarads, 240 microfarads. So we add these things up with the calculator and we get this answer. Now the problem is students will write this down and say, oh, that's my answer. I've got it in microfarads. However, I didn't pay attention to the units here. These were inverse microfarads because they're in the denominator. And I just called them microfarads here when really they should be microfarads to the minus 1. And the reason is I've forgotten to do this last flip. So if I do 1 divided by this, then my units will be microfarads and my answer will be 21.82 microfarads. So this is the real answer. So you have to be careful doing this. The two big ways people lose points on tests, they forget this or they mix up the formulas for series and parallel. Unfortunately, when we look at resistors, we're going to see these formulas swap. So there's a little bit of just sort of memorization that you can't get away from.